Okay, this is lecture 2, part 1. We're going to talk about, or at least start talking about, section 7.4, the inverse Laplace transform. And we start off with this fact. So if the Laplace transform of a function y1 is equal to f, and the Laplace transform of another function y2 is equal to f, and both y1 and y2 are continuous, then they have to be equal. So showing why this is proving it, or even giving a proof sketch in here, is beyond the scope of what we can do. To show this, you need advanced calculus. So need advanced calculus to show this. So we're just going to take it for granted in this class that this is true. And what this is saying is that, well, remember that an operator like the Laplace transform is just a function. You plug things into it and then output comes out. And the only thing that's different from a normal function that you're familiar with is that you're plugging functions into it and new functions come out. And for ordinary functions from calculus, you remember a concept called one-to-one. And that's something that you need if you're going to have an inverse function. And one-to-one means that if you plug in two different things, you have to get two different things out. And that's what this fact is saying. It's saying that the Laplace transform is one-to-one. That if you plug in two different functions, then their Laplace transforms have to be different, provided that we're just plugging continuous functions in. Okay, so it's a one-to-one transform, which means that we can invert it. So that leads us to our definition. So given a function, capital F of S, if there is a continuous function, has to be continuous, a continuous function, little f of t, with the Laplace transform of f, little f, equal to capital F, then little f is called the inverse Laplace transform of capital F. And we write that, the notation for it is that little f equals script L inverse of capital F. And so one thing that we get out of this, it's important to remember, is that if our function f is continuous, if we have a continuous function, little f, then if we take its Laplace transform and then do the inverse Laplace transform, we get little f back. Okay, so let's do an example. Okay, so let's consider this initial value problem, y double prime minus y equals negative t, y of 0 equals 0, and y prime of 0 is equal to 1. Now this is an example that we can solve already, so we don't need to use the methods of this section to solve it, but we're going to in order to just illustrate the method. So we know already from our existence and uniqueness theorems that there is a solution, y. So there's this unknown function y which satisfies this equation. Okay, so ignoring for the moment the initial conditions, just look at the differential equation. We have some function y, some unknown function, for which this is true. All right, so if these two, so the left-hand side is a function, The right-hand side is a function, and these two functions are equal. So if these two functions are equal, then their Laplace transforms are equal. So we can take the Laplace transform of both sides. On the left, we have the Laplace transform of y double prime minus the Laplace transform of y. And there I'm using the fact that script L is linear. And on the right, I have the Laplace transform of negative t. Okay. So we're now going to start using the material from the previous sections. You might want to pause the video and get these tables out of the book and have them to look at them while you're watching. The important tables would be table 7.1 on page 356, and that lists some common Laplace transforms that we worked out. And the other important one is table 7.2 on page 365. That's the properties of Laplace transforms that we worked out in section 7.2. So we're going to be using all of that in these examples. So you might want to pause and get that ready so you can see it while I use it. So the first one we're going to use then is the property, that tells us what to do when we want the Laplace transform of a derivative. So this is the second derivative. So using that rule, we're going to have that this is s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. Okay, then we have minus the Laplace transform of y. And all of that is equal to the Laplace transform of negative t. And for that, we'll use the table, 7.1. So the Laplace transform of t is 1 over s squared. Script L is linear, so it's negative 1 over s squared. And now we can solve this for L of y. So collecting all the L of y's together, I have s squared minus 1 times script L of y is equal to, and then we'll put everything else on the other side. So we have s times y of 0 plus y prime of 0 minus 1 over s squared. And now before we move on, let's see if I can make this blue, we can use our initial conditions. So if we go back, y of 0 is 1, y prime of 0, y of 0 is 0, y prime of 0 is 1. Okay, so here we have 0, and here I have 1. All right, so that means that this is then equal to 1 minus 1 over s squared. I'm continuing to solve for L of y. So L of y is 1 minus 1 over s squared times 1 over s squared minus 1. We could put that first expression over a common denominator, so s squared minus 1 over s squared times 1 over s squared minus 1. Right? Then that just simplifies to 1 over s squared. Okay, so I have that the Laplace transform of y is 1 over s squared. And, well, let's write this out here. Y, this unknown function y, we know that it's the solution to the given differential equation. In particular, we know that it has two derivatives. And in particular, that means that it's differentiable. Well, if a function is differentiable, then it's continuous. So since y is continuous, we can use the formula from just before this example that says that y is equal to L inverse of L of y. We just figured out what L of y is, so y is L inverse of 1 over s squared. And now we look at our table to see what that is, and that's just t. So y equals t is the solution to our initial value problem. Okay, so this last step involved just looking at the table. We have 1 over s squared. Okay, what function gives us a Laplace transform of 1 over s squared? And we just looked on the table. Sometimes it's not as easy as that. So before doing more differential equations, let's do examples of figuring out inverse Laplace transforms. So Our first example, let's say capital F of s is 2 over s cubed, and we want to know the inverse Laplace transform of that. All right, well, let's just write it out here. So we still want to use the table, but we want to make that thing inside the curly brackets look like something from the table. Okay, so the thing from the table that's got a power of s on the bottom is the third line on table 7.1. And if I really want to make it look like exactly like what's on that table, then I should write, instead of 2, let's write that as 2 factorial. So 2 factorial is equal to 2. And instead of s cubed, let's write it as s to the 2 plus 1. Now it looks exactly like what's on the table. On the table we have n factorial over s to the n plus 1, and the inverse Laplace transform is then t to the n. In this case, n is 2. Okay, so that one was pretty straightforward. They aren't always this straightforward, but that general principle applies. You want to make the thing look like something from the table so you can figure out how to use that table. All right, here's another one. Say f of s is 3 over s squared plus 9, and we want the inverse Laplace transform of f. Okay, well, so what do we have here? L inverse of 3 over s squared plus 9. If we want to make it look like something from the table, then we're going to want to write that 9 as 3 squared. So it's 3 over s squared plus 3 squared. And then we look on our table, and on the table we've got a b over s squared plus b squared. And for that line in the table, the inverse, or the inverse Laplace transform is the sine of bt. Our b here is 3, so sine of 3t. And that last part is coming from our table. Okay, that one's kind of straightforward too. All right, here's one maybe a little less straightforward. All right, so let's take f of s equals s minus 1 over s squared minus 2s plus 5. And we want the inverse Laplace transform. Okay. All right, so for this one, we want to find something on the table, make this look like something from the table. Well, we do have, in that last line of the table, we've got an s minus a over s minus a squared plus b squared. And the numerator looks like that. The denominator does not look like what's on the table, but the denominator in our example is a quadratic, and the denominator in the table is a quadratic. So the trick here in this example is to make our denominator look like that one, and we do that by completing the square. So our numerator is going to stay the same. If you want to complete the square there, you take the negative 2, divide it in half, and you get negative 1, square that and you get 1, and you want to add 1. Okay. But then you can't really change it, so it's supposed to be plus 5, so if I've already done a plus 1, I need another plus 4. And now I can write that as s minus 1 over s minus 1 squared plus 4. But 4 I can write as 2 squared, again to make it look like what's on the table. Now, that one I can read off from the table. So now I see the Laplace, the inverse Laplace transform of f, reading from the table, is going to be e to the t times the cosine of 2t. Okay. Now, this L inverse the inverse Laplace transform, this is also an operator. You plug functions into it, you get new functions out of it. And it happens to be that this operator, L inverse, is also linear. And we can use that fact to our advantage to do more complicated examples. So here's one. Let's take f of s, capital F of s is 5 over s minus 6 minus 6s over s squared plus 9 plus 3 over 2s squared plus 8s plus 10. And we want to know the inverse Laplace transform. All right, well, our capital F in this problem is a sum. And so by that linearity, I can write that L inverse of F is 5 times L inverse of 1 over s minus 6 plus, or minus, actually, let me undo, minus 6 times L inverse of s over s squared plus 9 plus, and I can factor out a 3, but I can also factor out a 2 out of that denominator, so 3 halves L inverse of, 1 over s squared plus 4s plus 5. Okay. And now we can do those individual Laplace transforms. So the first one, you can just read off of the table. We have a 1 over s minus a on our table. It's the second line on the table. The inverse Laplace transform then is e to the at, so this is e to the 6t. Okay, we can also read that second one right off of the table. So minus 6 cosine of 3t. Thinking of that 9 up there is a 3 squared. And then that last part, we can't really read that off the table. We're going to have to do like in the last example and complete the square in that denominator. See, because on the table we've got quadratics, but those quadratics have no linear term. There's no s term. There's just an s squared term. And you always get rid of that middle term in a quadratic. The way to do that is always to complete the square. So if I complete the square there, let's see, I got a 1 here. Completing the square will give me an s plus 2 squared. So that's s squared plus 4s plus 4, and I need an additional 1. And of course 1 I can think of as 1 squared, and now that one I can read off of the table. So copy these ones. And then that last one, reading it right off the table, is because of the plus 2, I've got an e to the negative 2t out front, and then otherwise I've got sine of bt, and b is 1 here, so sine of t. And there's my inverse Laplace transform for that one. Okay. Lots of examples here in this section. All right, let's try this one. Capital F of s is equal to 5 over s plus 2 to the 4th. And we want the inverse Laplace transform. All right, so we want to make this thing look like something from our table. So first of all, let me pull that 5 out. So I've got 5 times L inverse of 1 over s plus 2 to the 4th. Okay. Now I look for something on the table that is similar looking, and you can find it there. It's the third line on that table. But in order to match the table, I need a 3 factorial on the top. All right. But you can't just add numbers wherever you want. I cannot change what is inside those curly brackets. So if I want to add a 3 factorial on the top, I also have to put one on the bottom, so I can write this as 1 over 3 factorial times 3 factorial over s plus 2 to the 4th. and now pull that 1 over 3 factorial out, and I've got 5 over 3 factorial times L inverse of 3 factorial over s plus 2 to the 4th. And now it looks like something from the table, and I can read it right off. That 3 factorial is 6, so I have 5/6 there. And reading it from the table, well, if it didn't have the plus 2, then the inverse would be t cubed. Because of the plus 2, I get an e to the negative 2t out front, and then I have my t cubed. Okay, here's another one. All right, we're going to do capital F of s is 3s plus 2 over s squared plus 2s plus 10. And again, all these examples, I'm looking for that inverse Laplace transform. All right, so this one looks familiar. We've done ones like this already. We need to complete the square down there in the denominator. So I have s squared plus 2s plus 10. Right, and I can complete the square by writing that as s plus 1 squared. So there's s squared plus 2s plus 1, and then I need to add another 9 to make it match. So my f of s is, then I can rewrite that as 3s plus 2 over s plus 1 squared plus 9. Well, now things are a little different. I can't read this off of the table. If there were a constant on top, then I could read it off of the table. If there was an s plus 1 on the top, I could read it off of the table. If there was something like 5 times the quantity s plus 1, that would also be okay, because I could pull the 5 out and then read it off of the table. But here, I'm not in that situation. So what I need to do is somehow work an s plus 1 into that numerator. So here's one way to do the algebra on that. 3s plus 2 is equal to, and the trick that I'm going to use here is just write s as s plus 1 minus 1. It's sort of like completing the square, only it's completing the what? The linear. I don't know, that's not even a phrase. Okay, now multiply that out. What do I have? 3 times s plus 1 minus 3 plus 2. And I've rewritten it now as 3 times s plus 1 minus 1. And I can put that in my numerator. So now I have capital F of s is equal to 3 times s plus 1 minus 1 divided by s plus 1 squared plus, let's write that 9 now as 3 squared. Could have done that at any point previously. And now I've got the s plus 1, and now I can split that fraction up into multiple fractions. So I have 3 times s plus 1 over s plus 1 squared plus 3 squared minus 1 over s plus 1 squared plus 3 squared. I'm almost there. Now, you know, when you get used to this and you do these examples, some of this algebra you'll do mentally, but I'm trying to show every step along the way. So what I've got right now, I've got these two rational functions, and the first one I'll be able to read its inverse Laplace transform right off of the table. The second one, not quite. For the second one, I would need to have a 3 in the numerator in order to read it off the table. So let me make one more step, where I add that 3 into the numerator of my second fraction. So this one can stay as it is. It's ready to go. And this one I'm going to write it as minus 1/3 times 3 over s plus 1 squared plus 3 squared. And now both of those I can read off of the table and write down my answer. L inverse of f is equal to 3 times e to the negative t cosine 3t minus 1/3 times e to the negative t sine 3t. There we go. Okay, so these examples illustrate a lot of the kind of issues that can come up when you're trying to do this and the sort of algebra that you're going to need to think about and be experienced with. So you want to look carefully at these examples. We've got a lot more to come in this section, but the video is long already, so I'm going to stop this and we'll pick up in part 2.